Hey everyone, this is our next lesson on tangent lines, continuing our chapter on circles. So this is lesson 10.2.4. As usual, some prior knowledge going into this lesson that you should have. The basics are a circle. Do you know what a circle is? And you know what a line is. Keep in mind this is not a line segment where we would have endpoints. This is a line that is continuous with the arrows as the indicator of that. So with that knowledge, jumping into the first problem, problem 88, what are the different ways a circle and a line can intersect? All right, so it's very possible that the lines do not intersect at all. So here's an example of that. I drew them specifically like this, but I could have drawn the line somewhere else, like over here. Either way, this line, if it goes on forever, will never touch the circle. Another example of how they might interact with each other is with one intersection point. So in this case, here we have the line that pretty much just touches the circle at one point. And so in this case, because there's only one intersection point, we call this specific line a tangent line. All right, so this is kind of key for us, tangent line. That's something you should know. And in the event that the line crosses the circle twice, so have two intersection points, it would look something like this, where we see these two intersection points. In this case, we call this a secant line. Right, so those are the two types of lines that you need to be familiar with. We've kind of seen the secant line before, except this is with a line segment, and we call this a chord. But in this case, we're looking at a line that goes through the circle. It still has the same intersection, so it still acts as a chord, but it keeps going. And so we're going to be focused on a tangent line and seeing maybe how we could use this information going forward. All right, so now we're going to see how that kind of the inside of the circle might interact with the outside stuff. All right, so the next set of notes is kind of summarizing the next couple of problems, just to kind of speed up the process here. So here's something you definitely need to know. So focusing on the tangent line, like we talked about in the previous example. So here I have a circle with center C, and I have this line we call line L, cursive L, and it only intersects once, so we call this a tangent line. And so this point of intersection is what we call point of tangency. So tangent, tangency. All right, so if someone gives you the point of tangency, that automatically tells you there's a tangent line, and that's the point of intersection of the circle or whatever object you're talking about. And so what's special about this is how it relates to the diameter. So I've also drawn in a diameter that cuts the circle in half, but you should also notice I've drawn it so it's perpendicular. So it's 90 degrees with the tangent line. And so as I stated here, the tangent line is perpendicular to the diameter that intersects at the circle at its point of tangency. So I could draw in a different diameter, but it's not touching the point of tangency. But as soon as I draw one that touches this point P, we know it's going to be perpendicular. So with a tangent line, technically what they're trying to tell us is you have a perpendicular line to the diameter. right, if you want that, if you need to use that. So that's what we're going to use moving forward. All right, so something else in this lesson, I'm just going to go over it briefly. I'm not going to go into details of this, but just some vocab words that you should be familiar with. Circumscribes, inscribed, those are words addressed in an earlier chapter. I think it was chapter 8. So I'm just going to describe kind of what's going on here. We have 3 points that were given to us, point A, B, and C on a coordinate plane. And we connect these 3 segments to form a triangle ABC. And so if I connect these 3, but I guess this problem, what they're asking us to do is draw a circle that goes through all 3 of those points, A, B, and C. And so what I needed to do was to determine the center of that circle. And so what I did is I took, let's say, BC, and I found the midpoint, and I approximated the midpoint, and I drew a perpendicular line that goes across. And then I did the same thing with line AB. I approximated the midpoint, drew a perpendicular line, and the same thing with AC. I found midpoint and a perpendicular. So this is an approximation. So my circle's somewhere right here. You'll notice all 3 of these intersect in one point. And so that intersection is the center of the circle. And so from here, if I drew the circle, it should be the same distance around it. And you'll notice it goes through points A, B, and C. All right, so that one, it's not a topic we discuss much, but I just wanted to go over it. It's something you kind of have in the back of your mind if it comes up in a later problem. So the circle circumscribes the triangle, meaning it goes around the triangle but goes through all the vertices. Right. Triangle ABC is inscribed in the circle. So inscribed, kind of like an inscribed angle, you'll notice, except we've created a triangle, so it's inscribed in the circle. All right, so something to keep in mind. The next problem actually has 3 parts, A, B, and C, that are more like a test question you might see. All right, so here we have, let me zoom into this one. Segment PQ is tangent to the circle with center C at point P if PQ is equal to 5, PQ is equal to 5 and CQ is equal to 6, then what I want to figure out is what's CP and what's the measurement of angle C. Alright, so the first thing I would probably do is fill in some information. So PQ is this line here, so I'm going to put this as 5, and CQ is equal to 6, CQ is equal to 6, and the one piece of information, doesn't seem like a lot, but it's important, PQ is tangent to the circle at point P. So PQ, they're telling us this is a tangent line. So if that's tangent, then this segment must be perpendicular. And so hopefully once I add that in, you notice what we've created here is a right triangle. So this circle is really just a right triangle problem. So if I want to figure out what CP is, then you'll notice I have a right triangle problem, which is a Pythagorean theorem problem. All right, so then I would do, so CP squared plus 5 squared is equal to 6 squared. So solving this, we can have 25, 36, and then so CP squared is equal to, and so 36 minus 25, that'll give us 11. And so CP must be equal to the square root of 11. Alright, so that means now we know this is square root of 11. And the measurement of angle C, so C would be here. We want to figure out how do we find that measurement. Well, since this is a right triangle, technically we could use inverse trig. So if I say this is theta, then I would probably do maybe this is opposite. So we're going to use sine of theta is equal to 5 over 6, which means our angle must be the inverse of 5 over 6. Alright, so I'm not going to go over reviewing our inverse trig. I'm assuming at this point you're familiar with that. You might need to review your notes on that. So theta is approximately equal to, and so you would find that decimal. So I don't have a calculator with me, so I'll let you calculate that one. And so that gives us our measurements. So CP, and if we want an exact answer, we could leave it as an exact answer, or calculator will give you the approximated. Alright, let's see. Alright, so the next one we have circle with center H. We're given an arc, measurement of arc dr. So dr, I'm already looking for dr in the diagram. So this is 40 degrees. GOR, measurement of GOR is 210. So GD or DR, GOR, and we're looking for a few things. So GD, OR, and let's do RGO. Alright, so those are the measurements we're looking for. So I would probably start with labeling, the ones we do have. So let's see, DR we said was 40. GOR, so this one's a little bit tricky. GOR, so this starts at G, it goes to O, and then to R. So this, we're talking about this arc here. So don't make the mistake of going from G, it's not G, sorry, GOR, this would not be your arc. So just say arc, GO is not part of an arc, GO would be your diameter. So, or if I go this way, GO, there is no R to go to anymore, we've passed it. So make sure you're going in the right direction. So for GOR, I'm going to highlight this, GOR, and this one's going to be 210. Alright, so if you notice something, we're missing a small piece of this circle. We have another arc that's missing, not given to us. So if that's something we could definitely figure out. And if I notice, they actually want us to find that. So all three of these should add up to 360. So that means this is going to be 360 minus the 210 and minus the 40 degrees. So that would be, this would be 110, I believe. 110 degrees. All right, so we figured out that one. So measurement of arc GD is equal to 110 degrees. OR, so OR is this piece. This piece happens to be a portion of the 210. So, and I happen to know since GO, looks like GO is cutting our circle in half. Half of a circle is 180 degrees. So from G to O is 180. Then what must I have in order to complete the 210? So this one has to be 30 degrees. All right, so that means GRO is going to be 30 degrees. Measurement of arc OR, I'll put OR is equal to 30 degrees. And now we have one more angle to find, and that is RGO. So that goes from R to G to O. It's the only angle we've been focused on. Everything else has been arcs. So you'll notice this is a inscribed angle, which means we want to look at the arc that it's associated with. Well, this is 30 degrees, which means the inscribed angle, if you remember from the definition, it's always half of the arc. All right, so that must mean that this is 15 degrees. All right, so measurement of arc RGO is equal to 15 degrees. All right, so there's a lot. This is a really good problem. You have to know a bit about major arc, minor arc, semicircles, inscribed angles. That's a good problem to review. All right, and then the last one is, you'll notice right away, hopefully you notice there's a triangle in the circle, right? A triangle inscribed in the circle with center E. So AC is a diameter. So they've automatically told us AC is a diameter in this, which is nice because when they tell us we have a diameter, they've told us they've cut this circle in half. All right, so, and I know what the measurement of half of a circle is. All right, so they've also given us the area of the circle, which is 289 pi units. All right, so we're probably going to use that information. Area equals to 289 pi units squared. And AB is 16 units, so 16 units from A to B. All right, so A to B is 16. Now, another thing to remember is when we have a triangle in a semicircle, this triangle is a right triangle, right? Because of the inscribed angle of ABC has an arc of 180 degrees, which means this has to be 90 degrees. All right, which gives us again, this is really just a right triangle problem. All right, so we're looking to see what's the measurement of BC and what's the measurement of arc BC. All right, so let's see. BC, how are we going to find that measurement? And how are we going to use the area? All right, so the one thing I remember is area of a circle is pi r squared. So if I already know the area, if I already know pi r squared is supposed to equal to 289 pi, then I can figure out what the radius is. And then the radius perhaps will help us in this problem. So let's divide both sides by pi, which leaves us with radius squared equals to 289, which then means our radius is equal to the square root of 289. So if we take the square root of 289, luckily this is a nice number, so this is 17. So 17 units. All right, so that means we found the radius, which is 17. Keep in mind, radius is just from E to A, and it's also from E to C. So that means we have 17 and 17, which then gives us a complete diameter of 34. All right, now we have two sides of a triangle, which means we could figure out what our missing side is. So let's see, we could use Pythagorean theorem again. So BC squared plus 16 squared is equal to 34 squared. All right, and if we do these calculations, 34 squared, see if I'm doing these right, 34 squared is equal to 1,156. 16 squared is 256, plus BC squared. All right, so if we take 1156, subtract 256, we have BC squared is equal to 900. And this is, BC square root, this is 30. All right, perfect. This is a nice number. We could have used Pythagorean triples also. That could have been another option, but it might not have been obvious, so that's why we used Pythagorean theorem. All right, so we found our BC equals to 30. We still need to figure out the measurement of the arc, BC, so that's this one out here. So probably, if I have an arc, chances are I'm looking for its inscribed angle. So again, we have a situation where we probably need to find the angle. So if we have a right triangle, again, we could figure out using inverse trig to figure out that missing angle. All right, so I'm going to use 34, which is the hypotenuse. All right, 34 is the hypotenuse, and 16, which is an adjacent side. So this is going to be our cosine. So cosine of theta is equal to 16 over 34, which means theta is equal to inverse cosine of 16 over 34. So if you put that in a calculator, and I think it gives you approximately 61.9 degrees. All right, so either way, if you just want to leave an exact answer, this would be a good exact answer. If not, feel free to use a calculator. All right, so there you go. There's a variety of problems. They all use old skills that are good to know. Look back at those. Probably need to see those a few times just to make sure you understand all of it. As usual, there's a review preview section to help practice. It goes from problem 94 to 101. The math notes in this section go over inscribed angle theorem, which is a good topic to review. We used it in this lesson. And as usual, everything else is a good review of prior topics. So hopefully this helped. And let me know if you have any questions. All right.